Today we're going to consider some of the abstract algebra that underlies matrices. In particular, we're going to consider the case of invertible matrices and the general linear group, and eventually work our way onto the transpose, triangular matrices, and then go down to direct sums. So we see that from our previous result that you can express any matrix product as another element. The matrix product AB can be represented by another matrix C. We see that it might make sense to consider this as a group since you have some kind of closure under matrix multiplication. That is, the composition AB and the product AB represents the composition of the linear transformations described by each of these matrices. It follows from some previous theorems that the linear transformation describing matrix A is an isomorphism if and only if the linear transformation has an inverse linear transformation. That is, we said it is isomorphic if it is a bijection when considered as a map between sets. And so if it's a map between sets, it has an inverse, and we'll associate this to the inverse matrix. That is, if and only if there is a matrix A inverse, such that A inverse is equal to A inverse A is equal to identity matrix. Such a matrix A is called an invertible matrix or non-singular matrix. A matrix that is not non-singular is of course called singular matrix, and we will sometimes refer to these also as not invertible matrices. Note that even not all square matrices have inverses. That is, the zero matrix, of course, has no inverse. This is because there is no invertible. There's the map from everything to zero does not have a bijection. Is not a bijection, so therefore does not have an inverse. We'll also note that a matrix like this does not have an A inverse, and we can check this by noting that A is equal to 0. Therefore, it cannot be an isomorphism because it has a non-trivial null space. These are examples of singular matrices. Remember a result from earlier that only elements with a trivial null space only matrices with a trivial null space have an inverse. On the other hand, the identity matrix is non-singular since it is its own inverse. Also note that if A is non-singular, so is A inverse, with the inverse of A inverse being A. We'll also note that if A and B are non-singular matrices, then so is their product, since to the product AB you can associate the element B inverse A inverse, and if you multiply this out, since matrix multiplication is associative, you'll get the identity matrix. Therefore, B inverse A inverse will act as the inverse of AB. Therefore, the set of non-singular n by n matrices is a group under multiplication because we've shown associativity, closure under multiplication, inverses, and so on, and distributivity, but that's not important for groups. And so if you consider this set, and also the identity element, if you consider the set of non-singular matrices, we have a group, which we call the general linear group over field F, and you write this as GL of n, comma F. That is, n refers to the size of the space you're considering, or namely, the size of the matrices you're considering. With this, let's consider the transpose of matrix. Once we consider the transpose of vector, the transpose of a matrix is defined to be another matrix, A transpose, where the ijth element of the transpose is equal to the jith element of the previous. You can think about this as flipping over the main diagonal. Thus, if AI is the ith column vector of the matrix A, then AI transpose will be the ith row of the vector of the matrix A transpose. If the matrix A describes a linear transformation A from Fn to Fm, then the transpose matrix will describe a different linear transformation from Fm to Fn. Note that this does not necessarily describe the inverse transformation, but rather something different altogether. We'll note that, for instance, that if you have a non-square, it's impossible for it to be the inverse because inverses are only described for square matrices since they're only defined for bijections. But in this case, you can't have bijection between two non-isomorphic spaces. Next, we'll note that if C is equal to AB, the entries of the matrix of the two matrices can be related by this sum that we've used a couple times now. And you can instead relate that equation as C transpose equal to B transpose A transpose once you take the transpose and considering the sum. This is easier seen if you just try to multiply it out. Therefore, transformation reverses the order of matrix multiplication. This is remembered in the common way as the product of transpose is a transpose of products in reverse order, in the same way that certain other facts are remembered, that the derivative of a sum is a sum of derivatives, and so on and so forth. The transpose of a product is a product of transposes in reverse order. Another notational convention that matrices use is that they can be decomposed into matrix blocks by splitting the array into subarrays. For instance, if you have an n by m matrix A, you can decompose it into 4 blocks in this following way, or you let A11 just be some k by k matrix where k is between the minimum of these two, and then you let A12 just be k by m by k, this be n by k, and this be n by k by m by k. A kind of decomposition in which A12 and A21 are both zero matrices is called a direct sum decomposition, where you denote that A can be represented as A11 direct sum with A22. If you have this case, namely that an n by n matrix can be decomposed by direct sum decomposition into up to n vectors, in which each of the component matrices, AII, is a 1 by 1 matrix, you call this a diagonal matrix, since all of its terms vanish aside from those along the main diagonal. This is shown here. And you can also do a very similar, there's also another one that comes visually, where you have a triangular matrix. Note, triangular matrix is still inside of a rectangle. However, the only non-zero elements form a triangle. That is, a matrix A is called lower triangular if aj equals 0 whenever I is less than j, so whenever you're above the main diagonal, or for whenever your column number is greater than your row number. Likewise, you can define an upper triangular matrix where these lower entries below the main diagonal are 0. We'll now connect the idea of a direct sum decomposition with that of a direct sum space. Recall that a direct sum of two vector spaces fm and fn is defined to be the set of pairs x, y of vectors where where x is taken from fm and y is taken from fn. I usually write this as a vector, including x vector and y vector vertically. Therefore, you have a natural identification of the direct sum with a larger vector space, which has dimension m plus n. If you have an R by M matrix A, which describes the transformation from Fn to some space Fr, and you have another one that describes something that goes from Fn to Fs defined by B, then you see that you can make another linear transformation out of both of these by using a direct sum, which you can write as a R plus S by M plus N matrix. This acts on this space. You'll note that this will act correctly in the sense that it has the correct dimensionality. And you define it in this way. A, 0 vector, B. I'm sorry, not 0 vector, 0 matrix. And you define this product in this way. This makes sense, because if we consider this as just a 2 by 2 matrix by 2 by 1 matrix, we'd see this element times this element plus this element times this element should give you this element. So it makes sense that this has to be the 0 matrix so that you ignore whatever the y vector is doing and you just have a transformation of the x vector. Likewise, you have the same idea for B. Thus, you see the direct sum of matrices acts naturally on direct sums of vector spaces, and you see how that kind of indicates how these are two compatible ideas of a direct sum. That is, if you have a direct sum, you can create, out of any transformation on each of them, a new transformation on the direct sum of them, and if you have a direct sum of them, you can clearly understand what space it needs to act on, namely direct sum of the domains of each of the individual matrices, direct summed against each other. With that, we have discussed a lot of things, so feel free to review, but thank you for watching.